Good morning. My name is Tom Milster. I've been a faculty member at the University of Arizona College of Optical Sciences since 1989. And it's my pleasure this morning to talk to you about optical engineering. And one of my friends, a historical figure, Joe Cool, is going to help me with the narration. So first, let's ask the question, what is cool? In my book, Joe Cool is cool. Joe Cool is a historical comic book figure from before I was in high school. As an example of Joe Cool at the university, you can start in the upper left where Joe Cool's hanging around the student union. And then Linus comes in and he says, "Hi, Joe. How'd you do in chemistry today?" Joe says, "That chemistry is a drag, man." Linus walks off and Joe Cool's thinking to himself, Joe Cool can't worry about chemistry when he's busy thinking about optical engineering. In a little-known variation of the comic strip, Joe Cool continues, "Don't take my word for it. Let's listen to a couple of my cool friends talk about what it's like to do optical engineering and be an optical engineer."
Start, 2, 1, booster ignition, and liftoff.
In the morning, I might get to talk with some engineers from NASA, advising them on what type of imaging systems to use in a satellite, and in the afternoon, I could be working with people doing cancer research. My name is Amy Franz, and I'm an optical engineer for Edmund Optics. I got into optics because of my love of both math and building things. Initially in college, I studied physics because it involves a lot of math and also a lot of hands-on lab experience. And from there, I got into the more specialized field of optics.
I love optics because of all the different fields in the world that it touches. I come to work every day and realize that the parts that I'm making go into all kinds of different products. My name is Andrew Fisher. I'm a manufacturing engineer here at Edmund Optics. And every day I come to work and make optics, just like this. One of the other projects we're working on right now has optics that go into a display for a motorcycle helmet. You can kind of think of it like playing a video game. It allows the rider to see their surroundings, but it also shows a map of where they are or maybe their current speed so that they don't have to look down at the motorcycle when they're riding. They can keep their eyes on the road and stay safe.
Hi everyone, I'm Stephen Briggs, biomedical engineer at Edmund Optics. I work with a lot of our biological, university, and chemical engineering customers today. With anyone who thinks they have cancer or there's a cancer test out there known as a biopsy, what you typically have to do is go into surgery and get a tissue section or a gland removed, and then that's tested. But what we can do in the optics field is use laser, use light, and use optics to look into the skin without cutting.
Here at Edmund Optics, we get to work on a bunch of really cool things. Some of these things might be things you would see in an Avengers movie. Fingerprint scanners, iris scanners. Hi, my name is Ken Barber. I'm the engineering manager here at Barrington, New Jersey at our corporate headquarters. I manage a group of engineers here, design engineers, project managers, and other optical engineers. A couple of other things that we do is working with companies that make a lot of the electronics that you use, like your cell phones or your computers or your televisions. And we work with these companies to help inspect those parts so that when they get to your home, that you'll know that they're going to be working correctly.
If you're really interested in optics, I would say continue loving science. Optics is really about science, and if you love science as you go through middle school and high school and even college, you can drive towards an optics career.
Now let's look at an example of graduate research at the University of Arizona.
We make not just big mirrors, but mirrors that have some difficulty that nobody else can make. We're making right now 2 big mirrors. One is the Giant Magellan Telescope primary, and it's made of 7 pieces, each one of which is 8 meters across. When we started this project, nobody had ever made anything like this before.
When I first came, I heard these alumni coming back doing presentations, and they say this is the center of the universe. And if you think about it, we're manufacturing astronomical telescopes. In a sense, we're going to use to probe the whole universe. There's no place else in this world No people can do the same thing. It would make me really proud.
These students, when they leave, they are really highly sought after because they've been through this. They've taken technology from an idea to something that I'll call hardball engineering. And so they're ready to go.
Thanks, everyone. Now let's talk about a few more cool examples of optical engineering. One of the most interesting things I've done over the past 30 years is to assist for the searching of life in the universe and space optical systems for that purpose. The artist rendition shown here is of the 30-meter telescope that's being built at Mauna Kea, Hawaii. That's 30 meters in diameter. 1/3 the length of a soccer field is the diameter of the primary optic used in that telescope. This telescope and other new telescopes and space systems are being designed and constructed to answer big questions like, are we alone? The required optical systems are very complex, and they can take decades to build. Also, it won't be long before we see the commercialization of space, where optics will play a big role. That's cool. Astronomers need optical engineers. One of the ways that astronomers sense for life on exoplanets, that is, planets orbiting host stars outside of our solar system, is to look for the presence of oxygen, ozone, water vapor, and other gases like methane in the atmosphere of the planet. The planets are very small and difficult to image directly. Another method is to use transit studies. In a transit study, the planet, here represented by a black circle, orbits in front of the star. When the light received in the telescope is plotted as a function of time, we see that the light level decreases when the planet is in front of the star, between the star and the telescope. And depending on the gas in the atmosphere, different wavelengths will absorb more of the starlight than others. So here shown as 3 bands, 1.8 microns, 2.1, and 2.3 microns. The indication is that the gas absorbing at 2.3 microns is of a higher concentration than the other gases. Looking at these spectroscopically resolved time traces, the astronomers can determine the atmospheric composition of the exoplanet. Now, the transit study, although it doesn't image the planet directly, it measures the chemistry of the atmospheres. And if we could image these planets over a 30 parsec distance with transit studies, we may be able to sense 1,000 possible Earth-like planets. Now, as a sense of scale, 1 parsec is the distance at which one astronomical unit, the distance between the Earth and the Sun, subtends an angle of 1 arc second. And to put that in perspective, the distance to Proxima Centauri, the nearest star, is about 1.3 parsecs. At 100 parsecs, an 8.5 meter diameter telescope collects enough photons per second from a sun-like star to detect atmospheric components in its exoplanet. An 8.5 meter telescope is a large telescope. It is larger than the largest single telescope aperture fabricated at the University of Arizona. So why do we need so many photons? The signal we are trying to detect is very small on a large background. about 1 in 10 to the 6 photons are signal photons. The noise in the signal is proportional to the square root of n, where n is the number of photons collected. Since the signal is proportional to n, signal-to-noise ratio is proportional to square root of n. And the more photons we collect, the more distant systems we can observe. It takes the equivalent of a 50-meter diameter space telescope to collect enough photons to study the 1,000 Earth-like systems within 300 parsecs over a mission lifetime. The telescope has to be in space because the atmosphere absorbs too many signal photons. Let's look for a moment at a current space telescope and a space telescope that's in its advanced planning stages. The James Webb Space Telescope, pictured on the left, has a collecting area of 33 square meters, and over its mission lifetime could search for possibly 1 to 3 habitable planets, with a maximum distance for life detection of about 14 parsecs. LIDAR, with a collecting area of 201 square meters, could possibly search for 30 to 60 habitable planets, with a maximum distance for life detection of about 50 parsecs. Enter the Nautilus array for sensing 1,000 Earths. Nautilus is a dream of astronomer Daniel Apai, and I've been assisting Professor Apai in the optical engineering associated with the individual telescopes. Nautilus is an array of ultralight 8.5 meter diameter lens-based telescopes, where there are about 34 individual telescopes in the array. Each telescope consists of a transparent lens called a multiple order diffractive engineered lens. It's housed in an inflatable balloon-like casing and has a solar panel for power. The effective collection area of the array is just less than 2,000 square meters, or about 10 times LIDAR. The telescopes can be targeted individually or used together for sensing the most distant systems. It is much more economical and practical than a mirror-based telescope array due to the ultra-lightweight, large diameter mode lens. It's estimated that the sensing capability of the array will be able to go out to 300 parsecs. Now let's look at a size comparison. Shown on the left is the diameter of the Hubble Space Telescope with an effective collection area of about 4.5 square meters. The James Webb Space Telescope with 25 square meters. The Ariel, a European Space Agency transit study telescope at about 0.64 meters. And an individual Nautilus telescope with a collection area of 57 square meters. Now let's look at how to launch the mode lenses into space. The ultra-lightweight mode lens enables the telescope to be compact into a much smaller launch container. With the application directed toward the SpaceX BFR rocket, which has a fairing diameter of about 9 meters, we should be able to stack about 15 of the smaller launch containers in a single fairing. In space, the balloon expands, providing the outer shell of the telescope, and lock-in struts provide the mechanical stability for the instrumentation and the mode lens. The solar cell film provides power to the telescope, with thrusters for angular momentum management providing the positional stability. The mode lens, shown here on the right of the expanded telescope, focuses to the instrument package near the center of the telescope. Now let's look at an artist visualization of a launch. As the rocket goes into space, the fairing is opened and the individual launch containers are ejected. The balloons inflate and the lock-in struts stabilize the mechanical portions of each telescope. After all the telescopes are stabilized, the Nautilus array can begin its function. The individual telescopes can target near objects within about 100 parsecs, or they can be used together in sectional arrays or as a complete array to sense planets out to 300 parsecs. The Apollo 10 mission in 1968 was the precursor to the Apollo 11 mission that landed humans on the moon for the first time. Apollo 10 had a mascot, and it was our buddy Joe in the persona of Snoopy the Beagle. Let's say Snoopy makes it to the moon. He says, "I'm on the moon. I did it. I'm the first beagle on the moon." What is moon dust made of anyway? It looks like sand. Hey, maybe we can make glass for mode lenses. Well, it's really not such a far-fetched idea. Manufacturing in space could enable observatories much larger than Nautilus and utility-scale solar concentrators for energy and heat production on the moon. Moon dust, regolith, can be processed to produce iron, aluminum, silicon, titanium, oxygen, and optical glass materials like magnesium fluoride, calcium oxide, aluminum oxide, also called sapphire, silicon dioxide, also called fused silica, and magnesium oxide. Aluminosilicate glass, which is commonly used for touch displays in your cell phone, tablet, and laptop computers, is a good candidate. With melting temperature of about 1130 degrees centigrade, it contains about 57% silicon dioxide, 20% aluminum oxide, 12% mag oxide, 5% calcium oxide, 4% barium oxide, 1% sodium oxide, and about 1% trace materials. The barium oxide and sodium oxide are not available on the moon. Without these materials, good aluminosilicate glass is made, but the melting temperature rises slightly, still within the manufacturing parameters of fabrication on the moon. Cool. Optical engineers are needed on the moon. Let's take a step back and think about what we've seen. We know that optical engineers are in very high demand for astronomical and space optics design, fabrication, and testing. We can look at applications for telescopes, instrument packages, and other space optics, including communications, earth sensing, and defense. In the near and the far future, optical engineers will be key to the success of the commercialization of space. We'll need to understand how to make glass in space for both structural and instrumentation purposes. We'll have to fabricate optical systems in space. We'll have to make solar cells and solar concentrators. And of course, large telescopes and their associated optical systems. Now let's switch topics and talk about superresolution. In order to understand superresolution, we need to understand how a lens works. A microscope used by biologists and other scientists uses a set of lenses and mirrors to form an image of an object like a cell onto a camera. Let's look at a single lens on the right-hand side of the screen. If we take light from a distant point object that has a wavelength lambda, the lens focuses the light from that object to an image point. If we look at detail at the image point, we see that it's not a single point. It's actually spread out, even if the lens was perfect, due to an effect called diffraction. We know that the diffraction spot size, which here is labeled d sub Airy, is given by a very simple formula, 1.22 lambda divided by the numerical aperture, where lambda is the wavelength of light and NA is the numerical aperture given by the sine of the marginal ray angle here, the half angle of the focus cone. Now, classical microscopes can't resolve features in the objects closer than about a half of the Airy diameter due to Abbe's diffraction limit, which is about 200 nanometers in the best case. In order to illustrate that principle, what I've done here is not just have one point object, but 2 point objects focusing down onto the camera. And the profile shown here is a profile of the camera signal. We see that the 2 points are very well resolved. We can see that there are 2 separate points there. Although in the center between the 2 points, the irradiance is not 0. If we move the points closer, we get to the point where the objects are just resolved. We can just tell that there are 2 points there. And if we move the objects even closer, we see that we can no longer determine if that's one object or 2, and the object is not resolved. Superresolution is imaging object features closer together than the Airy diameter diffraction limit. By modifying the microscope with some very cool optics, biologists see feature separations down to 10 nanometers or even smaller. Cool. Biologists need optical engineers. So what does it mean to be really small in comparison to Abbe's diffraction limit of 200 nanometers or about 0.2 microns? What we have shown here is a logarithmic scale of size examples going from about 1 millimeter in size down to 1 nanometer in size, with steps of 100 microns, 10 microns, 1 micron, 100 nanometers, and 10 nanometers in between. A typical ant is a few millimeters in size. A human hair, anywhere from about 100 microns up to maybe 150 microns in diameter. A large cell spans the range of maybe 20 microns to 100 microns. Bacteria are a few microns to maybe 10 microns. Mitochondria, which are the power plants of a cell, the subcellular organism, somewhere between a half micron and a micron. Viruses span the range of a little over 100 nanometers to maybe 50 nanometers. And in particular, we're interested these days in the coronavirus particle, which is anywhere from 70 to 90 nanometers in size and diameter. Smaller than that are proteins, maybe 10 nanometers in size. And then finally the small molecules, which are on the order of about a nanometer. So this diffraction limit determines the size of things that we can see with a microscope. Anything to the left of the diffraction limit is fairly easy to see in a microscope, and anything to the right of that line is fairly difficult to see with a microscope. And it's because of the wave nature of light that determines this phenomenon of diffraction that limits the resolution of the objects. Now, if you want to know more about diffraction, take my 505 class, and you should have a pretty good background in diffraction theory. About a decade ago, a pair of brilliant scientists came up with the idea of single molecule microscopy. The idea is shown schematically here. When we attach a fluorescent molecule to a protein of interest, say something like a protein that would be active during cancer, and if we illuminate the fluorescent molecule with light that activates the fluorescence, in other words, makes it glow, then by imaging the fluorescence, we image where the proteins are, which is of high interest to biologists. The problem is that if there's too much fluorescence, and if the fluorescent molecules are too close to each other, the proteins are too close to each other, we can't resolve them because of Abbe's diffraction limit. The idea here is to reduce the light level that activates the fluorescent proteins so that only a few fluorescent proteins are active at any one time. And if we do that, then there's a high likelihood that the proteins that fluoresce will be farther apart than Abbe's diffraction limit for any one frame of the camera acquisition. So each frame of the camera contains diffraction spots that are separated by more than Abbe's diffraction limit. And by measuring the centroid of those focus spots, we locate the exact position of the protein that could be much smaller than 200 nanometers. And by taking a series of images, the proteins randomly blink on and off so that we have a map of the protein location at each frame statistically correlated to their positions. And if we add up all that position information, then what we have is a high resolution of the locations of the fluorescent proteins. One of the scientists is Eric Betzig, who came up with this idea, along with William Warner at Stanford. They shared the 2014 Nobel Prize in Chemistry for this invention. I've talked to Eric several times, and he keeps saying to me, "I love photons." Right, Eric, photons are cool. About the same time as Warner and Betzig invented single molecule microscopy, Stephen Hell invented stimulated emission depletion, or STED microscopy. STED microscopy uses a very clever combination of optical components to see with resolution much smaller than Abbe's diffraction limit. One difference is that STED requires a scanning laser beam. The example on the right shows from the Zeiss website a comparison between a wide field image and a STED image. And you can see particularly in the area around this feature that STED microscopy reveals details in the object much finer than the classical wide field image. Let's review and discuss the role of optical engineers in biotechnology. First of all, biotechnology is one of the fastest growing technologies in the world. And optical engineering plays a critical role in many aspects of biotechnology, and engineers are in high demand. Some of the application areas include improved resolution for research, optical biopsies, endoscopic probes for cancer detection, intraocular components, spectroscopy and polarimetric imaging for tumor margin detection during surgery, and non-invasive probes for disease detection. Our final area of discussion today is what I call the amazing cell phone camera. Shown here on the right is an example from an advanced cell phone where the window here looks out the back side of the camera. And there's a prism here that rocks back and forth around this direction here to correct for motion artifacts in that direction. And the lens group here actuates laterally in the orthogonal direction to the prism in order to compensate for motion artifacts in that direction. The lens group also actuates along the optical axis here to correct for focus. And the image sensor is shown in the back here as a multispectral rectangle. One factor in why customers upgrade cell phones is the camera system. Additional functionality is enabled by adding camera modules. The camera for which this rendition shown on the right is representative is a system that has 3 cameras on the backside, a normal view, a telescopic view, and a wide-angle view camera, along with a flash detector and a distance sensor. That's a lot of cameras just on one side of the cell phone. A single cell phone camera module by itself has a very complicated lens structure, including multiple lenses, tilting prisms, diffractive optics, and other components. Cool. High-tech companies need optical engineers. Let's take a closer look at a cell phone camera module. In a multiple camera module system like the one shown here, we might have a normal camera on the front side and a telephoto and a wide angle camera on the back side, where each of those camera systems is a completely different camera. Now, instead of having to cart around with you a normal kind of a camera, a wide angle camera, and a telephoto camera, all 3 of these systems are combined into multiple units that fit within the cell phone. It's extremely difficult, if not impossible, to provide all those functions within one camera module. Remember that the cell phone is very thin, and the size of the cell phone in terms of its thickness is also a primary issue with consumers. So you want to make the cell phone very thin, and you don't have a lot of room to stick all these elements and components in a single optical system. So that's why we have to have more than one lens system, lens module in the cameras for these different functions. They are becoming much more complex very quickly, including multi-element lens modules, facial recognition, dot patterns, and even LIDAR, which is laser radar. So let's look at how an image is formed, recorded, and displayed on a cell phone. We start with the fact that the lens modules are separate imaging systems, if we have an object, light rays from that object are going to interact with the lens, which is going to focus those rays and form an image. And the image is formed on the image sensor here. So each camera module has those common components: the lens barrel, and the image sensor. If we remove those camera modules from the phone, here are just a tele and wide modules, and we take apart that combined system and take out the tele-lens components, we have a lens here, which is actually a multiple element lens. We'll show in more detail in a minute. And that's housed in a lens barrel. The lens barrel is actually smaller at the top than it is at the back. The lenses in the front of the module are smaller than the ones in the back. And the image sensor is here. Okay. And that image sensor is connected by a cable to the computer inside the phone. And then the computer renders, through some processing, actually quite a bit of processing, the image that we see on the front side of the phone for that module. Okay, so now let's look in detail inside one of these camera lens barrels. Shown in the upper left is a drawing from a recent patent, and it shows a system with 1, 2, 3, 4, 5 lenses in a single lens barrel. The lens at the bottom of the drawing here is actually the lens that faces the object. In the backside mounted camera, it'd be the lens closest to the object. And the largest lenses are in the back, near the filter and the image sensor. The filter is used to filter out the infrared radiation that our eyes can't see. The silicon image sensors are sensitive to light out to about a micron wavelength, but our eyes can only sense out to about 750 microns or 750 nanometers or so. So in order to make the image not look strange, they put a filter in there to filter out those additional infrared wavelengths. And then the image sensor is in the back here. Now these rays that you see or these lines that you see here, for example, here, here, and here, those are what we call optical rays. I showed a little bit of a very simple ray diagram in the last frame. And those are what the optical engineer will use in a program called a ray trace program to determine the quality of the system. It's used for optimization of the system, to shape the lenses, and to figure out how the system can be changed the lens shapes can be changed to provide higher quality images. And you can see that for objects coming far off axis, maybe from this direction here, that the light rays are focused at the edge of the image sensor, and for the on-axis rays here, they're focused in the center of the image sensor, which is what you want. And it looks like this design is a pretty good design, because the rays that come in from the different angles are all converging to the same points. 3 rays from each angle are converging to the 3 points here, or to the different field points here in the camera. Okay, well, this system is an example of a 5-lens system, but more commonly now the higher quality lens systems are 6 lenses, and maybe even more lenses in the future. The image on the right is actually, it's a different lens system. This is a micro CT scan, microcomputed tomography X-ray scan of a lens barrel. And it shows the actual components here in cross-section of the 5-element lens module. This is also a 5-element lens module. A little bit different design than the patterned on the left, but still 5 lenses, where the lens near the object is again the smaller lens, and the lens near the image sensor is the larger lens. And it's really interesting to see the complicated structure that goes into the mechanical mounting of these plastic lenses, and how these guys all go together and work inside the camera at all sorts of temperatures and humidities. And to me, it's pretty amazing that these things, so complicated systems, work so well, but yet they're so inexpensive. One of the newest technologies to make it into cell phones and tablets is laser radar, light detection and ranging, or LIDAR. So what is LIDAR? Well, here I've shown a cell phone camera and an object, our friendly object tree. The cell phone generates a light pulse, and I've shown that pulse as a blue arrow. The pulse makes it to the object after a certain amount of time, and the reflected light pulse is directed back toward the camera. Now I've colored the reflected pulse red just to indicate that it's the reflected light, not the output light, but the object doesn't actually change the wavelength of the light pulse. After some amount of time, the reflected pulse is received at the detector that's mounted on the cell phone camera. On the right side of the slide is a MATLAB simulation, where the top part of the simulation shows the light amplitude versus distance. And you'll see here in a moment a blue pulse representing the output light pulse, and 2 objects that are represented as little red circles at the top of the diagram there. And it's a plot of light amplitude versus distance, and we'll see that evolve over time. The objects will reflect light back toward the camera, and we'll see that also here. One thing I haven't taken into account is the decrease in the amplitude with distance, but I think it makes it more clear if we just kind of factor that out for now. And then the bottom part of the simulation is the detector signal versus time. So if we start with our output pulse, we'll see a reflected pulse here and then here. Notice that the distance is twice the separation of the objects. And then we don't see a detector pulse until the reflected light makes it back to the camera. So what we do in the computer of the camera is recognize this separation here represents the separation of the objects. And we can compute, knowing the speed of light in air, what that distance separation is. And then the distance from, or the time from the start of the pulse to the return of the first pulse is the distance from the camera to the first object. So the delay between each return pulse is measured and a distance is computed. Now for a three-dimensional scene, it's a little bit more complicated than a single light output pulse and a single pulse reflected received at the detector. We have to do something in order to recognize the resolution that we can achieve in the image scene. So one thing that we can do is scan the light pulse over the object field, scan the output light pulse. And another thing that we can do is called flash LIDAR. That's using a diffractive dot generator to image many points at one time back onto the detector at the camera. And both of these techniques are used. So, okay, so now let's look at a couple of videos. The full videos are shown in the video credits down below. I encourage you to go look at those if you'd like to see them. The video on the left is a video of the capture of the LIDAR information from an iPhone 12. And the little dots that you see are the sample points. Now in this video, I think the dots are actually infrared, so you don't actually see them with your eye, but this camera has the infrared filter taken off of it so that you can see the little infrared dots. And the each little dot here in the scan field is used by the camera to determine the range from that dot to the camera, and then all the dots together give you the range field or range image of the scene. And that information is combined with the actual camera to show the color, texture, and other information of normal camera scene, and those are merged together. The video on the right is a very cool Mustang where the pseudo color represents what in the scene is ranged by using the app. And then there's the rendition of the vehicle with its size and pretty good three-dimensional rendition of the vehicle. There's a chair, and then you bring up AR as augmented reality. Looks pretty decent replication there. Here's a picture on the wall, again scaling the size to determining the size of the object, and then hanging another picture on the wall virtually. And is it real or is it the copy? That's very cool stuff. Okay, so let's review and discuss the last section. We know that optical engineers are in high demand for this new commercial technology, including mobile devices, autonomous vehicles, augmented, virtual, and mixed reality devices, heads-up displays, and devices incorporating these technologies are in the early stages of development. My own feeling, this is not from a trade magazine or any other source, this is my own feeling, based on my experience in the optical data storage research field. My thought is that the current demand for engineering talent is at a premium, and I think it should continue for at least a decade for this new technology. It's just at its very beginning stages. So there's a lot of promise there. And finally, I don't want to end with a conclusion. I want to end with an encouragement. Where our friend Joe has some words to say. He said, I had a great time talking with you about my favorite subject, optical engineering, which enables technology ranging from seeing to the edge of the universe to nanoscale proteins in a cell. Check it out. A buddy of mine summed up the adventure you could have in an optical engineer. 20 years from now, you'll be more disappointed by the things you don't do than by the ones you did. So throw off the bow lines, sail away from the safe harbor, catch the trade winds in your sails, explore, dream, and discover. Courtesy of Mark Twain. I want to thank also Edmond Scientific and the University of Arizona for allowing me to use their YouTube videos. Thank you very much. Any questions?